So you're welcome to the another edition of our weekly get together on this how you can use AI machine learning in your various field of endeavor. So today we are going to revisit. Remember that we had several ways of applications of machine learning in crop production, and we had also practical demonstration in Weka. So today the same way we had several couple of ways application of machine learning in animal production. So today we are going to start by revisiting the animal production while looking at possibility of having a practical demonstration in Weka environment. If you can demonstrate it in Weka, you can also do it any other place. And I remember last week, we encourage those that join in that to follow the guidelines being provided in the platform, the WhatsApp group where we belong, so that we can try to revise some of what stuff we did in the past, especially the 4-week videos on the introduction to machine learning, very important and instructive. And also another 3 videos that demonstrated how you can build your first model in Weka environment. I believe once you are done with those 7 videos, you are good to rise as a pro in using machine learning for your predictive solution and other analytics work. So we strongly recommend this. However, today we are going to revisit the animal production stuff, and then we data set. I have to acknowledge the fact that it's been a very challenging time having data set in this animal production environment. So this is still one of the challenges a lot of people are facing worldwide. It's a worldwide issue when it comes to utilizing AI and machine learning. Data is the key. If you don't have the data set, there's nothing you can do. So, and usually we hope people start cultivating their habit of documenting their experiences. All those your experiences in the past, they become a very wonderful asset. As is popularly stated, that the next oil and gas is data. If you have data with data analytics and machine learning and AI, you can take over from your competitors faster than you ever imagined. It's not a theoretical stuff. It is already in practice. Now you see companies that started utilizing data analytics within few months, few years, they're on top of the list. So, however, a lot of people are yet to realize the importance of this data set. So we still throw away our data. Let us cultivate this habit of keeping our data as at when due. So cultivate the habit of keeping our data as we generate them. In our farms, poultry, get a logbook. That's the minimum. Even if you don't have a system, you don't have computer, let's get a logbook and start putting something there gradually. So the day you are going to need them, you'll be surprised how your past experience will be able to guide you to avoid trouble, disaster in your farm in the next season. So this is just a call for us, especially people in this field, professors and practitioners in agriculture, to let us cultivate the habit of documenting our experiences in form of a data set. This is going to become very handy sometimes for you and very useful. And we can also share it with others. Yes, we can also share it with others. We can publish it, and then others can also participate as a way of contributing to the knowledge pool. So today we are going to make use of more of a dummy data and then see how far we can go. As we all know, agriculture is an age-long means of livelihood of millions, if not billions of people. Feeding them every day. Egg production, we know how important egg is to a growing child. And then, so worldwide, what can we do to make it sustainable? The global demand is increasing every day. So with technological advancements in farming, machine learning and AI method can be leveraged to increase efficiency. Okay, we can leverage it to increase the efficiency and accuracy in decision making while reducing the risk and costs associated with agricultural operations. If you can take some preemptive decision that can prevent disaster from happening before your hens stop producing egg, there are some signs and symptoms in those hens, but we cannot see it as human beings until you get to farm one day. They refuse to produce. We start calling the veterinary doctor to come around to come and check. What can you do? My hen is not producing. We have imagine a farm that is producing maybe thousands of crates of eggs every day, getting there meeting only maybe 100. That is a big issue. Customers are waiting, children are waiting, a lot of things are on demand. So can't we have a kind of preemptive solution that will tell us something may go wrong next week, and we can take proactive decision to prevent it if possible? You see, it is not magic. It is, like we keep telling us, it is science. The science are there for us to detect, but we don't have that capacity as human beings to have it. But with the data analytics, it has become very important, very possible. For example, the popular customer shun. You see, it's very, very popular now. Everybody, every day, maybe some of your telecommunications providers, you get a lot from them offering you promotion, very, very special promotion. For the next 1 week, you have so amount of money for free. You think they just want to give you for free? Maybe because they see the shun prediction already identify you as a potential customer shun, that you may run away from their service if their service subscribing. They quickly start to entice you with what will make you not to leave. So when you get free data for like 2-3 weeks, you yourself will say, this is a rainfall. Then maybe you would decide not to go. Because a lost customer is a potential enemy of that company that you will badmouth them, especially with this age of social media. So you need to, companies want to be ahead of the game. That is the essence of preemptive solutions using AI. So in similar way, in our poultry farms, in animal husbandry, can we utilize this thing to be able to have an idea of what may go wrong? What amount of production are we expecting? Or is it possible for us to get if we do this? And lots of other parameters that we can actually use machine learning and AI to estimate. So we've discussed all this in the past, how you can have the overview of AI and machine learning in animal production. So if it has worked in other areas, I want to believe that animal production will not be an exception. We can do a lot of things there to improve productivity and efficiency, enhance animal health and welfare, reduce environmental impact, enable sustainable livestock management, and host of others. And we also talk about the precision livestock farming. So where we can use AI and machine learning to support real-time monitoring of livestock using IoT sensors, cameras, and wearables. We identify a couple of possibilities, like the automated weight monitoring. Weight monitoring is very important. However, if you have to be carrying the hen regularly, you scare them. When you scare an animal, especially poultry fowl, they may refuse to produce in the next few days. So you don't want to interact too much with them to avoid such a problem. With automated weight tracking device, just taking the video from different angles, you will be able to estimate the weight of an animal. Because of pre-trained, you already trained a model with known weight of those animal that look like this in this 3D camera, this is the way. So whenever new picture is being taken, the system will be used to, in real time, predict this animal is so weight. These are some of the stuffs we do refer to as the impossibilities that machine learning and AI is making to become possible. Because in the past, how can you imagine that you can estimate weight of an animal by just taking by taking photos? It doesn't make any, what is the connection between photograph and weight? But that is the level to which machine learning has taken predictive solution to. And in animal production, we need it a lot. So you can save a lot of cost of hiring people to come and do weighting the animal alone. Just to weigh the animal, you have to bring hundreds of people to the farm with the attendant risk to the animal, contamination, also for that. In feed optimization, also we identify how AI can predict optimal feed composition. If you overfeed the animal, they may not produce. That is the worst part of it. I got to know practically not long ago. Everybody think that the more you feed your animal, the more they produce. No. If you feed them too much, they will not produce. Especially the poultry fowl had little experience in this now. That when you feed them too much, they will stop production. And you feed them too little, they will also not produce. You have to have the optimal feed composition for them to continue to produce. So can't we use systems that can be able to tell us and estimate for us the appropriate way and time to feed them? And also identify when they needed the food actually. So behavioral monitoring, you want to monitor them to know something is going on. They're undergoing stress. Just get to your farm, you meet an animal already dead. What could we have done better? Monitor the temperature, heart rate, and movement, detect abnormalities and stress indicators, improve animal comfort and reduce mortality. And also for that things we discovered that we can do in precision livestock farming. However, as good as all these looks, data set is still a big issue. So we making a case for predictive machine learning solution to support animal production. So, and as we know, it's under our clarification series, let the data speak. Let the data speak. So without data, then we cannot really do anything. That's why it's very important. And once you get your data, remember, you're going to pass through this generalized iterative machine learning modeling framework, where you have your data, prepare your data, you have the feature engineering, if necessary, you have the algorithms, you have where the modeling takes place, you check your performance, you can always go back, as it becomes necessary. We'll be discussing this in the past 3 weeks, how to ensure you do it right, which is very important. You can check out some of our previous videos. We are not done yet on that, but later we'll come back to other discussion on that. Also here, we have the modified iterative machine learning model framework to support. We have the iterative modeling machine learning modeling framework to support let the data speak principle, like I said, which we have been discussing. So data preparation, feature engineering, data modeling, you have your algorithm, you produce the model, you may have to go back. While doing this, you do the hyperparameter optimization, which is tuning the parameter. You may have to change the algorithm to another one, start with simple algorithm, to complicated ones. Sometimes you may have to go back here if you're not able to get what you are looking for. Do data reduction, do data cleaning, data transformation, and a host of others. So today we are going to now look at a case study of a very simple data set, and then we will demonstrate it for us in Weka. The first thing is you have to get your data. Getting into the system, let me open. This is a data set. Yeah, I'm showing now a data set that consists, the name is egg production, 500 samples data, 500 samples. So I want to believe you can chat to confirm that you are seeing my screen. I'm showing an Excel file now. I hope it's visible. You can just kindly type it and let me know if it's visible. Okay, thank you very much. Yeah. So this is the data. You get your data set. Excel is there, even though Weka has its own standard ARFF format for the data, but Excel is the easiest way for you to do that because we're all used to it. Yeah. So once you have your data, you can see this data is having date, it's having number of hens, egg per hen per day, that is eggs per hen per day on the average. So mortality rate, feed cost, what is cost of the feed? We also have the total eggs produced on daily basis, and then the revenue. So we look at your data set, you will now say, okay, these are the information, these are some of the features are provided. And I think we're having like 500 samples. Yes, 500 samples. So this problem, from our little knowledge of machine learning, you know that this problem, we fall into what we call the regression problem. The regression problem. Because you have the total number of eggs produced per day, and then you have the revenue, which is subject to a lot of things going on out there. The price of egg may go down if there are a lot of supplies and nobody to buy it. That's the law of demand and supply in economies. And sometimes it may go up when there's no production and the demand is so high, so the prices may also go up. And other things also may be responsible. If there's a sudden change in the cost of fuel, as we know, especially in countries that depends more on the gasoline for their everyday transportation, any change in the oil will affect the price. So what will be the case once you have your data? You put it in and then try to see, okay, you can do the first one to start doing some descriptive analysis. How is the data looking at? What is the average of number of hens? So what's the average? What's happening to those eggs? So what is the number of eggs per hen per day? You can see this is on the average on daily basis. So we have the mortality rate, the feed cost, and then the cost of the feed is very important. It's the cost for feeding. That is assuming that the cost of the feed also is constant because it may keep changing. So this is why I would have loved to have here, instead of cost of feed cost, I would like to have amount of bags of feed or kilogram of feed utilized on daily basis. You see? So because that's why we need to think of the features we want to produce, we want to generate. This one now is telling us the cost of feed. If we use it as features, the cost of feed varies. Maybe if the feed went up, if it has gone down again, even though they are still eating the same number of bags of feed, but they will be having different costs because the prices are going up and down. So it will be great in future if we have people who has data set that has the amount of bags of feed consumed per day. That will go a long way because we can always calculate the price any day. But as it is now, we don't have an idea of the amount of bags of feed these animals consumed because of the price. Except if they say that throughout the period of this collection of data, the feed remained constant, the price of the feed remained constant. So I'm discussing this so that I can educate us to know what we look for in our data. But notwithstanding, we can identify, we can be able to say, okay, we want to know the total number of eggs produced. We can estimate that, can use it as our first target. Let's predict, given some of this property, what is total number of eggs we can produce per day. See, looking at the mortality rate, looking at the eggs per hen per day, and then number of hen. Yeah. You can know that something will give you out. We call them collinearity. You can see number of eggs. If I know the number of eggs per day, I know the number of the number of eggs per hen per day. This can give me an idea of. So that's why let's take it in. Let's bring this data into Weka to make it to get practical with what I'm trying to explain to us. Get your data in there. So you go to Weka environment. You click the Explorer. So the Explorer will bring you to the Explorer side. Click the Explorer. Yeah, done. Yeah. See, you have to open the file. See, this is under the process. Every other thing in Weka remain gray out because there's no data. Until you bring in the data, before you can use all the others. So you have to open the data file. See where is the data store. Let me look for my data set. Assume weekly classes. You can see here, this is where I put the data, but then I cannot see the data because look at this for the sake of the people joining. So the file type is looking for is ARFF, which is the normal format for Weka files. So it's looking for it. So you have to change it here. Let me see my CSV file, Because you must have saved your Excel in CSV file format. Weka does not support the normal Excel, but once you make your data in Excel, save as, then you should select CSV data file. And then you click it, you can see now, data that were not being shown before they have become very much visible now. So it's because it's now looking for CSV data files. So this is the one I'm using. So these are the one we use for crop production, crop yield in India states. See how we're going to use this. Then we click it, open. Now the data is open. Now you are in the Weka environment. So you have the date. And when you click it to show you the count, some of the characteristics, number of ends, tell you the count, the characteristics. You can see egg per end per day. It tell you the minimum, the maximum, standard deviation. These are called descriptive statistics of the data. You can get it from here. You can also do it in your Excel file. It tells you the minimum, the feed cost, the total eggs produced, and also the revenue. You see, you can see the number of ends, minimum, maximum, mean, and standard deviation. So now, this is the raw data we have. We now decide, okay, we want to estimate total egg produced. We want to estimate. It may be that, okay, you want to know the revenue. What is the total revenue that I can have on a daily basis, subject to those things I have. But if I know the total number of eggs produced, I believe revenue can be easily calculated, as the case may be. So in that case, I can remove revenue for now. Let me try to estimate total number of eggs that I'm going to have. Given that I know the feed cost that has been invested into it, the mortality rate is known, the egg per day is known. So what's going to be the total number of eggs that I'm expecting to have for a particular future, So in that case, the date also we say, okay, does it matter? Can we remove the dates? So let's say you may decide to remove the date. For sure, we will not need the revenue for now, because if you want to model revenue, then you remove the total number of eggs, as the case may be, except you are trying to predict the market price for eggs on daily basis. You want to forecast the next 2-3 years or next month what's going to likely be the price of eggs. So to remove this, you just go here. You can see here, you remove revenue. You can see I remove the revenue. Now I'm left with 6 attributes. This is the one I want to estimate, total eggs. You can always bring it back. See, you can go here and say undo. Undo. The one you remove will come back. So it's only removing it from the platform here, from the Weka platform. It's not removing it from your file. Your original file is there on your hard disk. So remove this for now. And usually the last on the column, the last on this in this particular list is the target. And that's why when you prepare your Excel file, make sure the one you want to predict is on the rightmost side. Otherwise, you may be predicting the wrong thing. So once you know what you want to do, okay, we can go here. If I like, I may want to remove the date. I see the date. Does it really matter? I may want to remove the dates. So, and then let's now use 1, 2, 3, 4, 4 features to predict the total egg produced on daily basis. Okay, you go to classify. Then you choose, let's start with a very simple one, which we call the k-nearest neighbor. We call them lazy classifiers. Choose IBK, which is, you can see here, once you point to it, it shows you a description. K-nearest neighbor classifier. Click it, you have chosen that. Then the next thing you do is to decide how you want to run the experiment. Do you want to use crowd validation? We want to use percentage split. Let us use percentage split to make it faster, because cross validation, we run the experiment 10 times and find the average. For percentage split, let's say use 70% of the data for training. Automatically, it use the remaining 30% for testing. So we can run it. See, you can see it's done. This is the correlation coefficient. So it's able to predict correctly the total number of eggs that will be produced on daily basis to a correlation value of 0.578, mean absolute error, root mean squared error, relative absolute error. When I see the correlation coefficient, it means it's very, very poor. It's still poor. That is like 57% correlation. And the root mean square error is still very high. You see, the lower the root mean square error, the better. The higher the correlation coefficient, the better. So, however, the next call you have to think of is, okay, why am I getting very low performance? Here you have to click here. This is the k-nearest neighbor you are using. It's a simple classifier. You do the parameter tuning. See, this is the first point of call. You do the hyperparameter optimization. The default value is k is equal to 1. There are 2 hyperparameters. All these are called parameters. Batch size, number of decimal places. That is the number of decimal places you want your result. All these are parameters, but they are not hyperparameters. The hyperparameters are those that affect the performance of the algorithm itself. And there are only 2 here. One is the number of k you want to use for your computation, which is 1, set to 1. We can try many numbers. Want to try 3, want to try 4, want to try 5. And also the distance function. The default value is Euclidean distance. So we can make it to be Manhattan, Minkowski distance, shape distance, and also for that distance measure. You can also come up with your own distance measure later. Okay, so we keep this one now for now. Euclidean is the default for this, but we'll first of all start changing k. We change k to 3. Okay, run your experiment. You can see that the moment I change k to 3, it has increased to 71%. That is correlation. And simultaneously, the root mean square error is getting back down from 300 to 244. It means there's hope of getting better result as I increase the value of k. You keep noting down the values. Let me put 7. You can try 5, but because of our time, 74. You keep changing it. It's increased also. Let me try 11. You keep drawing down until it goes back, it goes down again. Once it goes down, then you identify the best one. 78. It's still increasing. This is what we call hyperparameter tuning. Let me try 15. Number of k. Okay. Run again. 78.35. Maybe 17. We make a difference. 70.35. You keep noting the value. 37. A little bit of increment. It's still increasing, though very minor. You keep changing it until there's no more change or it goes down. You see, there's no more change now. It seems it has reached its own pinnacle. You see, you have to, this is called hyperparameter optimization. We're able to get maximum of 78%, and this one reduced to 217. That is the root mean square error, mean absolute error. They are all very important, but these two are very important in determining your performance. 1 and then 2, root mean square error. They are very popular. And the way to do is you look into literature. If someone worked in that area before, look at the performance measure they are using. Then you need to match your own with them. If something important is missing, you can add it to your own. But for comparison of your work, it's always good to check literature to see what people are using in that area when they do modeling. So that is performance we can get. Yeah, we'll get ins again and then try to change, since it seems that with 17 we are getting the best so far. So you go in there and change the distance measure. Let's use shape distance. Okay. And then we run the experiment. You can see with shape distance, it brought it down. From 77, it came back to 76. So we quickly rush back and say, hey, no, this one is not working. Let me, shape is not working for us. Let's go to Manhattan. You try all those options. It has increased. Manhattan took it back to 78. Better than Euclidean. That is called hyperparameter optimization. And this is the manual form of doing it. You keep one constant while you change K. 1, 2, 3. Once you get the best K, then you go back to the distance measure and start changing them. So we're able to get 78%, 78.25. It's still low, but for K-nearest neighbor, that is fine. Once you are done with hyperparameter tuning and you still don't get what you are looking for, it is time to now say, okay, maybe I need to use another algorithm. You can go in there again. Let me use decision tree. Maybe 3. Let's say, why is these are 3, group of 3. Maybe I use a simple decision tree, the M5 tree. In this case, I run the experiment. It's also giving me almost something similar, 78. We also need to start the hyperparameter tuning. So in this size, we are looking at the number of instances to be used in determination at a point in time. It is 4. You see, number of instances. You have to keep changing it until you get the best. This is how you select different algorithm. If things get really tough, we're not getting what we want, we go to function where I'm going to select the SMOREG, that is support vector machine, one of the very powerful algorithm. So I go with that, I run it. It's getting 77. I try to do hyperparameter optimization. I change 1 to as many values as possible to see if I can improve the result. And also, I can also change the polynomial kernel. The kernel is polynomial. I can make it not to be polynomial. I can make it to be RBF and see if it will work for me. You can see 78. It means the data set is a little bit tough data. We are not getting 99 like we used to get. You see? So we have to see, okay, what can we do? A quick one I would like to mention before I forget is you can see that it's just telling us, giving us some of these results. That we are not really seeing the output. It's good to see the output yourself. Let's see the output. Then we ask what are the options we can try next to increase our performance. Maybe the features are not correlated well. Can we reduce the number of features and build a new model? Another way to check. That was why I show us different things you can go back always to do. But before I move there, let us I want to see the result, the actual predicted value here. Because of timing, let's use the K-nearest neighbor again. It's faster. So I want to see the result, the actual result. So you go here, more option. You see, you say, show me output predictions. It's null. It's not showing me the actual predicted value. I want to see it to be able to appreciate what this model is getting. So you have to specify what you want. I want it to be in plain text. You want it to send it to CSV file so that you can open it in Excel, that's fine. But for here, we want it to be in plain text. It will display it in this platform. Okay. Now, when I run the model now, you can see here, nothing is on top. When you run it again now, you're going to see this is the result. You can see it has shown the actual prediction. So it gives you a real idea of what you are getting. This is the actual value. We are predicting the number of eggs to be produced per day. This is the actual value given in the Excel file we are using. Your prediction is saying instead of 2,951, it's predicting 2,554 with the error of this. This is it. It is this error that I used to calculate root mean square error. You can see this one very close together. Only 7-point difference. See, even there is a case here, no point different. This is testing set, by the way. It predicted 2,608 as 2,608. It means it got this prediction perfectly right. So another way to show the performance, what you are getting is, take this thing, take it to Excel file, and make a plot. Plot the actual over the predicted, and see how close they are. This will also give you the idea of how your model is doing. So this is how we can show or use a very simple machine learning algorithm to estimate the amount of egg to be produced given the available parameters. Because of our time, next time we are going to look into, we'll give room for people to see clarification in case anything is not clear. We're going to try to check what if we remove some variables, feature selection. You see, we want to say, okay, feature selection. Can we remove number of hens? Maybe it's not contributing. Can we remove this? And I also show you then, by God's grace, how do you calculate correlation of each feature to the target to know which one should you focus on, which one is more important, which one is less important. You see, once we go, okay, we found out that the feed cost is not very important. Because when you have 1, 2, 3, 4, we have 4 variables. Ordinarily, we're supposed to have 10 raised to power 4 samples. 10 raised to power 4 samples. That's like 10,000 samples. But we are dealing with only 500 samples with 4 variables. This is called cost of dimensionality. The more the number of features, the more the number of samples needed. But in real life, the samples the number of samples are always constrained. This is what our client can provide for us. What can we do? We can only reduce the number of features. Sometimes when you reduce the number of features, you may be surprised that from 78%, it jumped to 98%. It means with 2 features, you are able to get better result. And the lesser the number of features, the better. It means it's easy for you to collect few data and be able to do excellent estimation. Unlike having 4 that cannot take us to 9, even not even 80%. So all this, by the grace of God, we've tried to look at them in our next presentation. We'll still continue with this by that point in time, inshallah. So this is where we're going to stop for the day. And like shortly before we stop, again, I will refer us to this. Yeah, to this. Yeah. So where I believe we can see my screen now. This is very important. This is what we are demonstrating. See, we built the model, we started the data, we did the modeling, we shared the performance measure. We didn't like it. It's not yet to what we are expecting. So the first thing is hyperparameter optimization. So always keep this thing with you. Keep it with you. Hyperparameter optimization. After we are done with it, we change the algorithm. Yet, we are not getting it. We still have some option here, making assemble, making hybrid, but not yet. Don't go down yet. Go back a little bit. Maybe you can make your data better. Why don't we do data reduction? Can't we reduce the number of features? Which is where we are going to start, God willing, by next week. So that we see if we reduce the number of features, can we make the result better? And that's also demonstrate something to us in what we have shown today in Weka. Classification problem is easier compared to regression problem. Because in regression, you are predicting actual value. It's tougher compared to just categorizing things into groups. If you remember when we did the crop production experiment. Any data we uploaded, we're able to get 98, 78, sorry, 80 something, 90 something easily. But for regression, it's not like that. Regression is tougher compared to classification. Of course, it also depends on the data set. But we're going to see how can we improve this performance to like 90 something through feature selection. Maybe we need to do normalization of the data. Maybe we need to check if some of the samples are bad. Maybe there's noises in the data so that we can be able to do what? To reduce them and to treat the data appropriately through what we call data cleaning and also for that things we can do. So I want to believe this is a good place to stop for the day. Thank you very much for listening. We can take a few questions because of our time.